Hey, it's Dr. Ron England coming to you again. EGN3443, Probability and Statistics for Engineers. Moving onward, and we're moving to two samples. We had one sample, now we got two samples. So let's talk about what we do in the situation where we've got two samples and we need to guide some sort of hypothesis of how we're going to compare them. All right, well, we're going to first start with this wonderful t-test. The independent samples t-test. And what we're looking at is two samples, and we want to know if there's a statistical significance between the two samples. That's simple. The characteristics, the groups aren't related or paired. You're assuming that it's a normal distribution. We'll talk a little bit about what to do if you can't assume a normal distribution in a little bit later. But we got these two separate groups, and we want to compare and say, hey, is there a statistical difference between them? So what do? We use the independent sample t-test. Straightforward hypothesis, the population means are equal. The null hypothesis being the population means are equal, and the alternative hypothesis being the population means are different. You calculate the t-statistic, and I'm going to do an example calculation by actually solving a problem in this case. So here's a good sample problem. This is a typical sample problem. I've got group A, group B, and we're looking at a new fertilizer to see if 10 plants have more, less, or the same level of growth. The hypothesis being that they would be the same. And we want to kind of look to see what would happen if there actually is a significant difference. So I typically solve this using Python code. And there really is one key piece of code here, and that is the t-statistic and the p-value, which is done by t-test_end, which is part of the stats. Oops, I didn't move the group B heights down to a separate line, but you set the two heights up into an array, and you can feed both arrays into, these are numpy arrays, by the way, and you can both plug them into the built-in function t-test_end, and you can get the t-statistic and the p-value back. Now, one of the things that I would do is I would do a comparison. In this case, a box plot kind of shows me what I want to see. And I would also do the calculation of the t-statistic and the p-value. And the box plot kind of makes me look like, those look pretty different. Those quartiles look pretty different on that box plot. And if you do calculate the t-statistic and the p-value comes out to 0.00059. And your comparison p-value would typically be 0.05, which would be that 95%. And 0.00059 is 2 decimal places to the right of that. So you would say that there's a pretty low probability that you'd observe such a large difference between the plants that it wouldn't be, so essentially what you're saying is you're going to reject the null hypothesis in this case, at least at the 0.95 level, and state that there actually is a statistically significant difference in the heights of them. So that was just a really quick and dirty example. And you can see it really wasn't that hard to do. It's not doing the calculations that's a challenge. It's actually looking and making sure that you can interpret the results. And remember, that is what we're trying to do. It's really easy to ask the AI to generate some Python code to do a comparison test between the two. It's actually very easy to ask the AI, what comparison test could I possibly do? And then generate some Python code, run it, but getting that final set of calculations and then looking at what those values mean is the important thing. So where would you use this? Well, often used in clinical trials, and the clinical trial, which is almost the exact same example of our plants, would be the random versus the actual medication versus the placebo. But there's also anytime you make some sort of change to a population and are comparing the two different methods against each other, the independent samples t-test works quite well for what you're doing. And that's probably going to be 90% case for everybody, this is what you're likely going to do. However, there are other methods that you need to do. You need to know about at least. First, the paired samples t-test. And this one actually would probably be the one that you would do not as frequently as the independent samples t-test, but if you were going to do this one, this would be the second one. And what it does is it looks at an analysis between different pairs. This one's kind of got a use for it when you're dealing with the same subject, which would actually be, there would be no other subject variability, hopefully, between the same subject underneath two different scenarios. But what you do in the methodology is this. It's very straightforward. You got the hypothesis, but when you take the calculations, and I'm kind of just really going into this last little bit here, the before and after treatment scenario. So you say you got a situation where there's a treatment, and you want to look at before the treatment and after the treatment and look at some value. You did something, you've got another set of values. And instead of looking at a direct comparison of the two different samples of before and after, you take the difference of the samples. So basically you pair the samples up and you calculate the difference. Now you can see why that actually makes sense when you're dealing with a change in a scenario with a single sample. So it would be like, a good example is, one of my favorite examples is the cognitive impairment of lack of sleep, where a person actually is well rested and does some sort of activity, and then they make them go without sleep for 2 days. I know this one pretty well because I actually participated in a number of these, and then see if they can actually, how well do they perform. The control is that it's the same individual, but the comparison is before and after sleep. Now, the nice thing about this is because you're taking the difference in before and after, you can just use the standard, the standard test that you did before. So you're just going to do, you don't have to do a paired samples test. So that is a good, I mean, this is one that you're probably going to do. So when I'm saying, what do you do to do the comparison? Well, you can go right back over to the previous lecture and look, well, are you setting to see, because suppose you're looking at the difference, is the mean of them 0 or is the mean of them actually significant value? And you've actually got you've got variability to work with. So I'm not going to do an example of that one. There are, by the way, some examples in my class notes of this specific situation. Now, here we're going to go a little bit further with the good old F-test. And the F-test is good for comparing variances. Look, remember, we're not necessarily, in this case, we're not comparing means, we're comparing the variances. Now, one of the things that the F-test is used for a lot when you're looking at multiple samples, it's a preliminary test. And you do this before conducting t-test to verify that the variances are equal, because one of the assumptions of that two-sample t-test is that you've got equal variances between the different samples. And so this can be used as a filter for that. But it is useful for comparison of the sample variances. So the big thing is the pre-test validation, testing the homogeneity of the variance before you do either a t-test or an ANOVA, which we haven't actually looked at. It's also useful for the comparing precision between two measurements. So it's got some usefulness. So in the quality control field, or in the pre-test validation, this is one. And I'm not going to give you, again, I've got samples of this specific test in my notes. I'm trying to keep my lectures short and focus on the different tests and what they're useful for, rather than a bunch of samples, because I give you samples in the notes section of the class. Proportions, okay, of course we've dealt with proportions, and the technique here, there's actually multiple tests for proportions. Now again, you're doing a comparison of proportions between two populations and groups, and not the situation that you had in the previous lecture where there was the proportion in a single group to see if it actually met a criteria. This case, you're looking at the differences between the two. So you're looking at the frequency of an outcome to see if it differs significantly between two different groups. And in this case, you've got a number of techniques that you can use: the two proportion z-test, the chi-squared test of independence, and the Fisher's exact test. Which ones are you going to use? Well, you're probably never going to use the Fisher's unless you're actually getting really into the weeds in your statistical analysis. But a two proportion z-test or a chi-squared test aren't out of the question. Those that you would do. Now, am I going to show you the calculations for those in this lecture? I am not. I've got, again, samples of those. They're very easy to look up. What are they useful for? For comparing proportions. Okay, so remember, I'm going back to what is important: that you can look at the scenario and determine the correct test. But for looking at a two proportion z-test, you're looking to see if the proportions are equal. There's a calculation process in here where you calculate the pooled proportion and you compute the z statistic. Okay, again, I'm not going to go through a sample, but I can give you, like, let's say you have 100 trials of one thing and 200 trials of another, and you had a number of successes in each trials, and you look at the percentage of each of those. You can look at those and, using this technique, determine whether that their equality, which would be the null hypothesis, is statistically significant. All right, so when to use it? One of the typical ways for that is the good old A-B testing scenario, group A and group B. That is a very common one. And then the other one, I don't do a ton of medical research, but the quality control is, am I getting a higher or the same or a lower level of defect in two different samples in two different sets of things that are going through a manufacturing process. Okay. Now, and if you go back to it, it doesn't look that much different from what we did with the original example. All right. Now, we're going to look at one thing here that I really see that's important is, and again, I don't know if you'll ever, I'm not going to give you this as one of the problems that you have. I've got enough problems that you're solving a lot of problems as it is anyway. I'm more, again, concerned, but the chi-squared test of independence. And it obviously can be used for comparing two categorical variables. But the beauty of this is it's able to work with more complex categorical relationships. In other words, more categories, where you can measure any deviation from something that's expected. So it's nice in that it can analyze multiple categories of something simultaneously. How are we going to use this one? I am not going to have you go through and do a chi-squared test of independence. In fact, really, what I'm going to focus on in this class are the first two that you actually saw in here, which was the independent samples t-test and the and the paired samples t-test. And those I will actually have you do some calculations of. But I would be amiss if I didn't at least show you that there are other tests that deal with multiple samples for differences in means and differences in variances. There's more than one. And that's looking at the fact that you've got standard data. But now looking at the concept of where you don't meet the parametric tests, basically meaning that you don't have normality and equal variance between the samples. Okay, so how do you deal with ones that don't have where you can't make the assumption of normality and equal variance with the samples? Okay, well, there are tests for that. I'm going to tell you right off the bat, we're not going to do any samples of non-parametric. I'm going to cover it because you need to know that there are tests that do exist to deal with these types of data. So the Mann-Whitney U test, okay, the Wilcox signed ranked test, and there's a few others, the sign test, Fisher's exact test, McNemar's test, and Kruskal-Wallace's test. What is important is that you do know that if the assumptions that we make in the test that I have covered, that sample normality, the distribution of the sample means would be a normal distribution. Okay, if those aren't met, there are other ways to deal with this. So I have covered that these do exist. So there are certain things that you need to look at when you're making those considerations of using non-parametric tests: statistical power, robustness, type of data, and sample sizes. And really the biggie that you deal with a lot here would be statistical power and sample size. Sometimes you just have really small samples where you can't even do an assessment of normality because you just don't have the data sets that you need to do it. There are tests that at least let you get some set of results for the validation of a hypothesis. So, which ones are we looking at here? Independent t-test, paired t-test, and z-test of proportions in this case, but z-test. Those are the guys that you really should actually look at. And what do you need to be able to do? You need to be able to take sets of data, samples of data, look at what they're samples of, determine the correct type of test, generate a null hypothesis, and be able to come to a conclusion. That's what you need to be able to do. Now, do you need to go into a lot of sets of data that are non-parametric or don't meet those initial assumptions? You need to know that there are techniques that you can use for those, but you would typically do those in a much more advanced statistics course. I've got to cover a lot more material in this one to make you go through all of those. They do exist, they're there. So what do we got here? Hypothesis test for two samples. Here's what I want you to do, be able to do. These are the ones. Independent samples test, compare two separate unrelated groups. Paired samples test, comparing related measurements, usually from the same subject with a before-after. And a proportion test, which is comparing outcomes between two groups where you actually do something and you got an outcome of X percent, or a certain percent being rejected, or something that makes it different from the remainder of the group. Remember, in each of these cases, you've got two groups. And these are the biggies that you should know how to do. Okay, this is it. And those are the ones I'm going to give you. Now, I may, if you request, this is my students, not my YouTube viewers, request examples of where and when to use some of the other tests, because maybe you are in a scenario where you need to know these other tests. For me to do those, I did a lot of dissertation work on comparison tests between groups in my PhD, and it was actually, was my PhD? No, it was a research after my PhD, but it was related, and went through many of the different types of ways of doing the comparison and handling the hypotheses. All right, I wanted to get this under 20 minutes, and I am going to achieve this goal with 5 seconds to spare. On out.